Welcome to Chemistry at Hanahega High School. Today we'll be looking at Chapter 6. Now, periodic table and periodic law. Periodic table has a very specific look to it, and as you saw in last chapter, it's really related to the electrons. Now remember, a group or a family is a column on the periodic table, and a period is a row on the periodic table. Now, the periodic table itself, period is related to the concept of periodicity, which is a tendency to recur at regular intervals. So a periodical is like a newspaper that comes out every single day. It reoccurs at a regular interval. Periodic law then is related to that. When the table is organized as it is, an increasing atomic number, there is a periodic repetition of chemical and physical properties. What that fundamentally comes down to is, because the table is organized by valence electrons, as we saw last chapter, that means when we wrap around in the periodic table to the same region, the same column, we have the same number of outer level electrons. And it turns out that outer level or valence electrons are the key to chemical behavior. So everything in that first far left column, in our S block, those all have one valence electrons. And the first family or the first column in our P block will have 3 valence electrons. So that's what it means by recur at a periodic interval. When you wrap around the table and come back to the same column, you have things that are chemically and physically similar to each other. Now there's a number of different ways we classify elements of the periodic table, and we're going to use most of them from time to time just in different situations. Now electrons, particularly the valence electrons, control many of the chemical and physical properties. That's why we have the same valence electrons. You have similar chemical and physical properties. And if you recall when we did electron dots, as we counted across the table on the S&P block, that literally told us exactly how many electrons we had in the valence level. Everything in the first column had 2, the second column had 3. The third column, which is the start of our P block here, where boron is the top of, those all had 3, and carbon 4, and so on. Now, other ways that elements can be classified. Well, one is by certain names on the table. And we'll look at a couple of different ways of naming certain regions of the table. Now, one of the important families that we've already seen before are the noble gases, the far right of the periodic table. In noble gas electron configuration, we were using the noble gases to skip a bunch of inner level or core electrons. And the noble gases basically have a full outer S and P sublevel. Now, the rest of the periodic table in the S&P block would be what are known as our representative elements. And most books will include the noble gases. Sometimes we treat it separately because when we say noble gas, we mean a specific group within the representative elements. And all except the noble gases, all the rest have partially filled S and P sublevels. Now, the D block in the middle of the table is our transition metals. So usually when we refer to the D block, we'll either call it the D block or we'll call it the transition metals. And they have an outer S that is full and a nearby D sublevel that we're putting electrons into. And then finally, the group at the very bottom of the periodic table, which we would call the F block last chapter, those are our inner transition metals. Because remember, they're inside that start of the transition metals up in the bulk of the periodic table, the main portion of the periodic table. So if we just cut our table between our S and our D block and push them apart, that's where our F block would fit. So like the D block, they have an outer S with electrons in it, but now we're putting in a nearby F sublevel. So representative, noble gas, transition, and intertransition would be one of our methods of classifying different parts of the periodic table. Remember, noble gases were the far right column. The representative would be the S&P block. The transition would be the D block, and the intertransition would be at the bottom where we had our F block. We can also classify things in the periodic table by properties. And this is an important one, and we use this right away in the next couple of chapters. The periodic table that we have on the wall, as well as the one I give you, if you look on the right side of the periodic table, starting in the upper right or left-hand corner of the P block, you'll notice there's a set of stairs. Well, everything to the left of those stairs on the periodic table behaves in a very similar way. There are a whole bunch of substances that basically lose electrons to become stable. They're all shiny, They're malleable, which means if you hit them with a hammer, they don't shatter, they just flatten out. They're ductile, which means you can draw it or pull it into a wire. And they're very good conductors of heat and electricity. Collectively, all of those things to the left of the stair step are metals. And metals all share these common properties. Now, to the right of the stair steps, we have the non-metals. And these are like the exact opposite of the metals. They're dull looking, not shiny. They're very brittle. Hit them with a hammer and they shatter. They're poor conductors of heat and electricity. And then we have the area along the stairs, minus aluminum, because aluminum is clearly a metal. And those are things that are metal-like. They're metalloids. They're on the stairs, so anything above or below a step, minus aluminum. And these things tend to have properties of both metals and non-metals because they're right at that transition point between the metals and the non-metals. So when you look at the periodic table colored in this way, our yellow would be our non-metals, the green would be the stair-step metalloids, and then the whole rest of the periodic table would be our metals. So most of the periodic table is metallic in nature. And remember hydrogen over on the far left there? That's not in our metallic part of the table. That's actually a non-metal. So that's the one thing. So consider the stairs as like going all the way over to the left. Hydrogen then is not a metal. So there's our stairs. And you can see the green things minus the aluminum are all above and below a step. The yellow are to the right plus the hydrogen, and the blue are to the left. Those are your metals. Now, we can also classify by families. Now, a family is a group of individuals that share some commonality. So elements can do the same thing. They can share some common physical and chemical properties. One of our most common and important family groups are noble gases. We've already seen these in a number of different situations in chemistry, and we're going to keep seeing them. Now, the group numbers are a way to describe which column or family we're talking about in the periodic table. And depending on what table you're looking at, the noble gases are either group 0, group 18, or group 8A. Now, far left-hand side of the table, so we're going from the far right to the far left, are alkali and metals. So this is group 1A, or group 1, minus hydrogen. All of these substances have one valence electrons, and they basically react with nonmetals to lose that electron very, very readily. Just to the right of them are the alkaline earth metals. Notice the commonality of the name alkali, alkaline. Alkaline means basic. And when we put any of these in water, it makes the water basic in nature, hence the name alkali and alkaline metals. Now, the alkaline earth metals are the group just one to the right. So the 2A, or the group with 2 valence electrons, starting with beryllium, those are alkaline earth metals. The way I think of it is the alkali is a short name, alkaline earth is a longer name, first one, second one. And then the only other family on the periodic table that is so chemically similar it deserves its own name, and we run into it from time to time, is the group 1 left of the noble gases, the group 7A group, which are called the halogens. Fluorine, chlorine, bromine, and iodine are halogens on the periodic table. And they're a group of nonmetals that are very, very chemically similar to each other. Now, anything else in the other, because there's 18 columns, so anything else in the other 14 columns, so to speak, they're typically referred to by the head of the family, the top of the column. So carbon is often referred to just as the carbon family. The ones underneath boron are in the boron family, and so on. So the rest of them really don't have names that are so common that we see them and we use them from time to time. So we just refer to them. Their family name would be the head of the family, the top of the column. So carbon for group 4A. Now, one of the things that are introduced in chapter 6 is the idea that atoms can gain or lose electrons to become stable and form what are called ions. So when we form an ion, cations and anions are basically atoms that aren't stable, and they've got one of two options. If they're a metal, they lose electrons to become stable and form a positively charged substance, a cation. Think of it as the T looks like a plus sign. So metals, by and large, on the periodic table, become stable through losing electrons in this way. So metals form cations to become stable. A cation is always smaller than the neutral atom because when we lose electrons, we have the same number of protons but with less electrons for them to hold on to. And we've often lost an entire valence level when forming a stable metal cation. So we end up with an atom or a species or substance that is significantly smaller than the original neutral atom. So cations are always smaller than their neutral atom. And remember, we lessen the number of electrons, that's less electron-electron repulsions. And this nucleus has a stronger pull on the remaining electrons, decreasing their size. And also, as I said, in many cases when we form a stable cation, we've lost an entire valence level. And if we're on a lower energy level, we're closer to the nucleus. So it also usually involves the decrease in the number of shells or energy levels. Now, the opposite of cations is anions, and this is what nonmetals do. They're going to become stable through the gaining of electrons to form a negatively charged ion or anion. Think of it as anti-negative against. Anions are always larger than the neutral atom, and that's because we have more electrons. That's increased the number of electron-electron repulsion with the same straight nucleus. So it's going to end up swelling in size. And that finishes up really our first set of notes and really all we're going to look at from chapter 6.